Hello everybody, how are you doing today? Happy summer. This is Dr. Heldman, TechTalk Education. One of the most important topics that we're dealing with today and will continue to deal with is the area of cryptography, keeping things secret and hidden from prying eyes. And so I wanted to go through and explain a little bit about how a certain cryptographic algorithm works. It'll give you a flavor for how mathematicians have accomplished this amazing work, and what it's going to do is ultimately play into our work with quantum computers as well, because quantum will be able to undo any of the cryptography that we're using today in a very rapid pace. It can't do that now, but it will ultimately be able to do that. And so people are actively working on quantum cryptographic algorithms. So what does that mean? Let's get started and see what this is about. Now, before we go too very far, I want to let you know I've had a lot of math training, and I'm not very good at math. So whenever I look at math and people start whipping out these huge equations, my eyes tend to water over. I have a hard time paying attention. So I had to do a lot of research for this. I've had some crypto classes before, and I really enjoy the subject of crypto, but it is not for the faint of heart. So I'm going to take my time walking you through one of the most popular cryptography algorithms. It's called RSA, and see how that works. Here's my goal. If you understand how this crypto algorithm works under the covers and you understand what it's trying to accomplish, the math is really not that hard, but it's very powerful. And so this is why it's important for you to understand it, even though you're probably never going to code up a cryptographic algorithm, or you definitely will use them. In fact, you are currently using them every day. So let's see what this is like. Now, I titled this Understanding RSA, and friends, with only a minor math headache, because there is going to be some math in here. I'm going to try to take it easy as I walk you through this. Let's get started. Now, cryptography is the art and science of hiding information, so only the right person can understand it. In this case, there's a person messing around with a cryptex. This thing is called a cryptex. I'll play this again for you. You can buy these off of Amazon. They're a lot of fun. You can have them open a door, a door to like a joy thing, things like that. You can think of this as writing a message in secret code, only your friend knows how to read. So that's the point with crypto. That's what we're trying to accomplish. There's two kinds of crypto we need to be aware of. The first one is called symmetric encryption, and that's where we only have one key. Now, the diagram on the screen there, I took this from a blog called What is Symmetric Encryption. It's a good blog. You should go out and read it. But the drawing here is showing you that you're at a laptop, you're composing a message. The message gets encrypted with a key. The key is known only to you and to the other that is grabbing that message. So in the middle here, you can see that after encryption, we have this really screwed up message. And then we are able to decrypt it using the same key, and we can read the message. This is like a shared key to a lockbox, if you think about it that way. Both the sender and the receiver use the same key. And so you could go, if you had two keys, you go to the lockbox, you open it, put the message in, close it, and then you give the key to your friend. He goes and gets the message and reads it. So that's symmetric encryption. So common symmetric encryption examples are going to include things like secure data transmission, which you use every day, twice on Sunday, file and disk encryption, secure messaging, meaning end-to-end encryption, wireless security protocols, financial transactions, database encryption, and application level tokens. Now, you might be wondering, well, what is encryption? Let me go back one second. When we encrypt a message, we just scramble it to get nonsense. That's what we're talking about with regard to encryption. Now, there's a way that you can go out and practice this yourself. It's a very old symmetric algorithm, and it's called the Caesar Cipher. And you should run out and watch this YouTube. Here's the link here for the YouTube. This guy's Paget Teaches. I enjoyed this a lot. It was a very good way of showing you how the Caesar cipher works. It doesn't work anymore. It's been cracked for a long, long, long time, but it was very clever, and so it will help you understand how symmetric cryptography works. Now, there is a thing called asymmetric cryptography, and you think of this as like a public mailbox. So we've got some characters here. First of all, I want you to know that Bob and Carol and Ted and Alice were taken from an old movie called Bob and Carol, Ted and Alice back in the day, and for some reason cybersecurity experts who write about these kinds of things like to use those names. So Bob here composes a message that says, "Hello, Alice," and he uses Alice's public key, this is called public key encryption, to encrypt the message, and this is what the message looks like after it's encrypted. So it says, "Hello, Alice." This also says, "Hello, Alice," but it's been encrypted with Alice's public key. He then sends the message to Alice. She uses her private key to decrypt the message, and she gets the message back. So that is what is called asymmetric encryption. When you think about asymmetric, the easiest way to think about it, it's confusing because A means, to me, it means without, but in this case it means two keys rather than symmetric encryption using only one key. So that's what we're dealing with. We're dealing with asymmetric encryption. Now I want to introduce you to RSA. So asymmetric public-private key encryption. The idea is we've got a public key, we've got a private key. This was developed by a guy named Whitfield Diffie. That is quite the name, isn't it? I love that name. He's on the left-hand side there. By the way, I think all of these guys are still alive. This all happened back in the mid-70s. And Martin Hellman. They both, and that's a great name, by the way. My name's Heldman with a D, but his is Hellman with an L. I think that's great. Anyway, those two were the ones that came up with this notion of public-private key encryption. Some people from MIT, some mathematicians from MIT, named Ron Rivest, Adi Shamir, and Leonard Edelman picked up on this, and they developed the RSA algorithm at MIT in 1977. So Whitfield Diffie and Martin Hellman came up with the idea in 76. These guys, Ron Rivest, Adi Shamir, and Leonard Edelman picked it up and ran with the ball and published that in 77. The RSA algorithm is still in use. In fact, RSA became an enormous security company. It's still around today, and is still in use, though there are other more powerful algorithms that have been developed since that time. And this is a note to you and to me. We have to keep an eye on quantum computing, because what's happening now, we've built everything around RSA and similar cryptographic algorithms, and yet quantum computing is potentially going to have the power to undo those things immediately. Like, these are very, very unbreakable right now. It's very difficult to go in and break one of these algorithms. You'll see the reason why here in just a minute. But when we have quantum computers and they're in the very high qubit value, let's say 1,000 qubits, for example, which is the goal that Microsoft and Google and IBM are working toward, it would be very, very easy to undo or to brute force this algorithm. So we're very, very interested in that. RSA is an asymmetric key encryption algorithm that makes use of public and private keys, and it's a good example. There's a way that you can set this up on your computer. You can set up an RSA key pair on your Linux computer. I'll use a different movie to show you how to do that, because this movie is going to take a little bit to get through, and I apologize for that, but the detail is pretty intense. Now here's what you do. The whole thing starts out with what are called prime numbers. I don't know if you remember back to your high school days. A prime number is a number that can only be divided by itself or 1. So 1 goes into a prime number just fine. The prime number itself goes into itself to create the number 1. That's a prime number. Now imagine that you use very, very large prime numbers and you multiply them together. The fact is that it's really going to be difficult to derive how I put these numbers together. So I've got this huge, huge prime number. It was clearly created by multiplying two smaller prime numbers together. How do I find out what those prime numbers are? It's very, very difficult to do that. So this is the interesting feature of prime numbers and the RSA algorithm. Now, it is extremely difficult and even impossible to figure out the original two factors. So that's something you've got to hang on to, that idea. Okay? Now, we're going to invoke, this guy was back in the 1700s. His name was Leonhard Euler. He pronounced like O-I-L-E-R, Euler. Some people might say Euler, but it's Euler. And this guy was a Dutch mathematician, and he came up with this thing called the Euler Totient function. And we're seeing some Greek in here. So now we're introducing Greek, which if you've had some math classes won't surprise you, or chemistry or whatever, physics. But in this case, if you've never seen this before, this little guy here is called a phi. It's P-H-I, but it's pronounced like F-E-E. This is the phi. So we're saying phi of n is going to be equal to one prime number minus 1 times another prime number minus 1. So in the case of our explanation here, we've got two prime numbers, 61 and 53. We take 1 off of each one of those, multiply them together, and we wind up with this magic number here, 3120. Hang on to that because we're going to need it. Now that you've derived a number from the Euler Totient function, in this case it's 3120, you need to find an encryption exponent E that has some very, very important characteristics. And the only reason I'm explaining this is not so you can sit down and write this yourself. This work's already been done, and indeed people are working on even more strenuous cryptographic algorithms. What I'm trying to accomplish here is just a basic understanding of how this thing works when it's doing its work for you while you're out on the web. We want to choose a number E such that the greatest common divisor, this thing is called the GCD, equals 1. So we're looking for the number 1. And we've got a formula here. 1 has to be less than E. This is the E that we're choosing. It's called the encryption exponent, the thing that we're going to use to encrypt. And that's got to be less than phi of n. So we're going to use some exponent, and the whole thing has to evaluate to 1. So there's a way that this formula here calculates the GCD is derived, and when we take these two together, we should come up with 1. So we need no common factors other than 1. That's the important part of this. What this is really saying is that the two factors that are going into this are both co-prime, meaning they exist together in equations, and they're both prime numbers. Now, a lot of people use the number 17. It's an easy number to remember. It's a prime number, only divisible by itself or 1, and it's handy for calculating things like the GCD, so that's why it's useful for us. So now we pop in the GCT 17 and 320 is equal to 1. In other words, we can go to the next step because we know that the only common divisor for these two numbers is 1. Now, that's important to us because we have to be able to do some more math on this thing and take what is called the modular inverse. In other words, we're going to invert this thing, and we're going to find a key D. So we've got E. We chose E as 17. We're going to derive a D, and this step would not work if we did not have it set up this way. Okay, now we're going to introduce you to another mathematician. This is Euclid you're looking at here. And so now we must compute private exponent D. So this is the thing that's going to make the whole thing work. And we're going to make use of a special math operator called the modulus. A lot of people call it the modulo. It means exactly the same thing. The modulus is fascinating. It's used in crypto. It's used in gaming types of situations, simulations, things like that is very, very important, especially if you're in a coder. Understanding how the modulus works is going to be really important. Now let's sum up what we know so far. We know that P is going to be equal to 61, Q is going to be equal to 53, E is equal to 17, and phi of n is equal to 3120. And we derive phi of n by using the Totient function, and we took 1 off of these and multiplied them together. So the standard formula that we're going to use, this is Euclid's formula. It's called the extended Euclidean algorithm. We're going to say that E modulus phi of n. So we're going to find the inverse d, and you got to hang with me on, there's a lot of letters going on here. We know e is 17. We're going to take the modulus of this number, and we need to find d using this formula. So this is the Euclid formula. And what this says, I don't know if you're familiar with this or not, when mathematicians have three bars like that, that means always equal to. So we're saying that our private variable d here is always equal to e to the minus 1 mod phi of n, and in this case it's 3120. So we know e, we know mod 3120. In other words, we're going to say that d times 17 is equal to 1 mod 3120. Well, right away, you're probably wadded up in figuring out, well, now how did this get here? Now we've got d times 17. What happened here? Well, we know that e is 17, and what we do is we're going to take the multiplicative inverse of this thing. I'll show you how to do that in the next slide here. But we know that we need to invert this thing. So e to the minus 1 isn't helpful for us. And what we're really trying to solve is we're trying to solve for d. All right, let's take a quick side trail here, quick rabbit trail, and let's find out how the modulus operator works. Now, I don't know if you were ever taught long division by hand in school. When I was teaching this, I'd teach this in class, and kids would look at me like, you're out of your mind. What are you doing? What are you talking about? But I'm going to use the old school because I came from the old school. And so what we're going to do is we're going to say, okay, we've got a number 48. We're going to take modulus 18. What does that mean? It means that we take the 18, put it on the left-hand side of this division operation. We divide it into 48. 18 goes into 48 twice. 2 times 18 gives us 36. We subtract the 36 off of 48, and we wind up with the number 12. That is the modulus. So you want to remember that the modulus is the remainder of any division operation. So that is why it's so useful. That's the modulus. Okay, now the extended Euclidean algorithm is called the EEA, builds on the standard Euclidean algorithm, and it not only finds the greatest common divisor, which is something that we have to have, of two integers a and b, but it also finds two integers x and y, such that this equation here, GCD of a and b, is equal to ax plus by. This is important in cryptography because it allows us to find what's called the modular inverse of a number, which is essential when using E to calculate the private value D. Now take a look at this. So this thing involves several laps. We're not going to exercise it just once. We're going to do it quite a bit, and our whole goal is to get to the number 0. So look at this. So we do a GCD of 48 and 18. That's equal to 48 mod 18 modulus 18, which is 12. Now we take the 18 and the 12 and we plug them in. We get 18 modulus 12 is equal to 6. Then we take 12 and 6. 12 modulus 6 doesn't have a remainder. It's 0, so now we can stop. So we're going to go around this. These are called laps. We're going to do these laps until we get to 0. And then what we're going to consider is the next one up. So we stopped here. We're going to consider step 2 here. And I'm going to label these as step 2 or step 1 or whatever, so you can clearly see, hopefully clearly see where we're at. I hope I haven't lost you. I can't begin to tell you how many hours I've spent researching this and getting it right, because I'm not good with math. Okay, now how the RSA encryption works, number 6. What we have accomplished so far, we know P is 61, Q is 53, N equals P times Q, which is 32 through 3. Phi of M we've calculated at 3120. E is 17, and now we want to calculate the private exponent D, delta D. It's not really delta, I shouldn't have said that, it's just D. To do that, we need to find what's called the modular inverse. So here's our original formula. D is going to always be equal to e to the minus 1 mod 3120. Got that already, we know the formula. Now what we want to do is we want to divide everything through by e to the minus 1. So you can see here that I've put d divided by e to the minus 1 on the left-hand side, is going to be always equal to e to the minus 1 divided by e to the minus 1 on the right-hand side times mod phi of n. And so then we know that the value of e, so we plug it into the equation. Well, now how does this multiplicative inverse thing work? What is going on here? There's a couple of ways, and when I was going through my math training way back in the day, I had calculus 1 through 4, diffie-q, linear algebra, some other things. I was lost most of the time. This is not my forte. It helps with music, though. It helps me to understand music. Anyway, e to the minus 1 divided by e to the minus 1 is always going to be 1. So any number divided by itself will always be 1. So that's why we wind up with 1 over here. So here is a graphic that shows you how this works. On the right-hand side, we've taken e to the minus 1 and divided it by e to the minus 1. This winds up equaling 1. But on this side now, what we do is we know that we're essentially saying 1 over e to the minus 1, which is the same thing as saying e to the minus 1 divided by e to the minus 1, minus 1 times minus 1 equals, and this thing equals 1. So we've used multiplicative inverse to find out that this thing just equals 1. That's how this works when we're doing the right-hand side of the equation. Okay, now this is a really noisy thing, and I apologize for this, but I wanted to get through this so you can understand that this thing uses laps to figure out where we're headed. So what we've accomplished so far is P is 61, Q is 53, we've got 32, 33, that's N, phi of N is 3120, the public exponent is 17. Then now we know this thing, D times 17 is 1 modulus 3120, therefore D equals 2753. How do we know that? How do we know that we came up with 2753? That's kind of strange. Well, we're going to use this extended Euclid algorithm to accomplish this work. Now take a look at this line. We're going to use the EEA equation, GCD of A and B, the greatest common divisor of A and B, is going to be equal to AX plus BY. We know that A is going to be 17 here, and B is going to be 3120, which leaves us with X and Y, and we set the whole thing equal to 1. If you've had enough algebra, you know that we can't solve one equation with two unknowns. So that's going to be a problem. So we have to solve for one or the other, either X or Y, and in this case we're going to choose X. Now we're going to use something called Euclidean Division, and I got really wadded up with this when I was doing my research for this. But the basic idea is that you take a dividend divided by a divisor, and you come up with a quotient and a remainder. So we can tell that the GCD of both 17 and 3120 is equal to 1 because only 1 can be used to divide evenly into both. We remember that 17 can only be divided by 1 or itself, as is 3120. So we're alleging that 3120 and 17 are equal to 1. Next thing we do is we divide 17 into 3120. We come up with 183 remainder 9. How does that work? Well, I've got another little graphic here. 17 goes into 3120 183 times. 183 times 17 is equal to 3111, and we have a remainder 9. Now I told you that 3120 is going to evaluate to 1. We could actually break that into other factors. So I misspoke when I told you that, because you could divide 5 into that and come up with something. But the point here is that we're going to go through this Euclidean division to find the number, and we're going to wind up using this remainder 9. Here's how this looks. So we say that the number 3120 is going to be equal to 183 times 17 plus 9. So the concept here is we've got these two numbers here, 183 and 17. We multiply them together, we add 9 on because that's the remainder, and this is our first step. This is step 1. Next, what you do is you take this resulting 17 here, bring it down here. That turns out that that is 1 times 9 plus 8, because there's a remainder associated with this thing. So the remainder is 8. Then we take the 9 down here and we say, well, that's 1 times 8 plus 1. Then we take the 8 down here. 8 times 1 is 8 plus 0. We finally gotten to the step 0. But now what we want to do, we want to back up to step 3. We're not going to park on step 4 here. We're not worried about this 0. We're worried about the next one up, step 3. We're going to concentrate on what's called the last non-zero entry. What we've accomplished so far, I'm going to sum up P61, Q53, you get it. We think the D is 2753. We're trying to figure out how we derive that number. So we're still going through the steps to calculate it. Now we're using EEA. It's the greatest common divisor of A and B is going to be equal to AX plus BY. We have to solve for X and Y. We can't have two unknowns with one equation. We've got to solve for one, then plug it back in to find the other. And then we have this handy little chart here. Okay, what does this tell us? Well, simply that we can iterate through the steps and we arrive at 0. Therefore, GCD of 31 and 17 equals 1. This means that its inverse exists, which is what we need to know in order to calculate D. The inverse of this must exist in order for us to be able to adequately calculate D. Okay, this is a really loud slide. I apologize for this so far. So we have to backtrack. We're backtracking up to step 3 here. To express 1 as a combination of 17 and 320, this is how we find the X and the Y in the EEA. We start from the last non-zero remainder right here, and we say, well, 9 is going to be equal to 1 times 8 plus 1. This is again in the form of Euclid division. We've got a divisor times a quotient plus the remainder. This is called Euclid division. We can rewrite this by taking this 1.8 section, this 1 times 8 section here, and we can move it over to the left side of the equation so that we wind up with Coolio 1. So this is 1 equals 9 minus 1 times 8. We took this entire thing, moved it over to the left-hand side adjacent to the 9, but that means when we move it over, you probably remember this from your algebra days, that we have to change its sign, so that's why it wound up with a minus sign here. So we're saying that 1 is going to be equal to 9 minus 1 times 8. Now, because in the extended Euclid algorithm our goal is to express 1 as a combination of early values, we can begin to rinse and repeat by first rearranging, plug in the previous results. So now we say 8 is going to be equal to 17 minus 1 times 9, and so forth. And so you can see the substitution that goes on here and ultimately solving this equation. So we're just, all I'm really trying to get across is there's no need to get wadded up in the algebra that's going on here. It's just good to understand that we're lapping through this, we're iterating through this process to arrive at a destination that we're trying to find. We want to find what D is. What we've accomplished so far now, and I gave you the thing again here, we say that 1 equals 9, 1 times 8. We went through this math here and reduced this down. Next, we rearrange the equation in step 1 right here to make it equal to 9. So we say 9 is going to be equal to 3120 minus 183 times 17. We plug the equation in, the equation we derived from the previous slide for 9, and we wind up with this. 1 is going to be equal to 2 times 3120 minus 183 times 17. And this whole thing is huge, and then you distribute it algebraically. And so I don't want to go through necessarily because it'll create a lot of stomach acid for me. But what I'm trying to get at here is that algebraically you manipulate these things to get, we're always trying to get to 1 here. So the result is going to be that 1 is going to be equal to 2 times 3120 minus 367 times 17. Bingo, look at what we've got. So we know, rearranging these things, our x here is going to be minus 367 and our y is going to be 2. So we were able to derive this number. What does that look like? Well, since we're computing the modular inverse here, where e equals 17 and phi of n equals 320, we only care about x, and since x is minus 367, we take its modulus. So we have minus 367 modulus 3120, and we wind up with 2753. Let's see if that works. I'll bring up the Windows calculator, and we'll see if we can make that happen. Now notice here that I'm in the scientific calculator. The Windows calculator is fantastic. I love this thing. You've got your standard calculator, scientific, graphic programming, and date calculation. We're going to use scientific because that's where the modulus operator lives. So we plug in 367, and we're going to change its sign right here. So we've got minus 367, and we're going to go with a modulus of 3120. Let's see what we derive here. 2753. Wow, look at that. That's very cool. So that actually works. Then, once we know that, we can evaluate everything to 1. So we can say 17 times 2753 modulus 120 equals 1. Therefore, 17 times 2753 is 46,801. 46,801 modulus 3120 equals 1. Bang, we're down to 1. That's what we wanted to derive after going through all of this math. Now the big things to keep in mind are all we're doing is we're using the modulus operator for sure. That's something you need to be aware of. We're using this lapping process where we're iterating down to get to 0. Things have to have a common divisor of 1, and then we get to the point where we solve for D. That's the way that we can decrypt this thing. So E stands for encrypt, D stands for decrypt. Okay, the happy result of this. We know that E equals 17, N equals 3233. D equals 2753, and N equals 3233. That's a number we started out with. Suppose now that we want to encrypt a message with these keys. Let's say that our message is big M equals 123. That stands for message. Not much of a message, I guess, but okay, work with me here. We're going to use a weird formula. So the formula says that M to the E mod N, and we're going to put in what we know. We remember that our message is 123, so we take it to the 17th power. Message to E, that E is 17 to the 17th power. We're going to take the modulus of 3233. We're going to wind up with this number here, 855. So when we send the message to Alice, our message is going to say 123 in plain text. That's called plain text. The cipher text, the actual encrypted message, is going to say 855. Finally, we come up with these keys. So we now have our 2 RSA keys. Our public key is going to be E17 N3233. Our private key is going to be D2753 N3233. Now suppose that Alice gets the message and she wants to decrypt it. There's a different formula, and this is probably the most work you're going to have to do, is memorizing the encryption and decryption methods. And this isn't going to be the only equation. There will likely be others as you're working with different cryptography equations. Anyway, the message is going to be equal to C to D. So D is this number here. I have an E there. I meant to spell out mod, but I said mode. I meant to spell out mod. I'm sorry for that. Mod N, so we can do 855 to the 2753th power. Mod 3233, that comes out to be 123, and that is the message that we originally sent to Carol. All right, how'd I do? So I'm not comfortable teaching math. It's really difficult for me to teach because I get so wadded up into it, and I get confused. I'll be up on the blackboard and I'll be confused about what am I saying here, and then a kid will correct me. You might have some corrections up for me, which is fine. I'm perfectly fine with that. But what I was trying to do is get across to you the elegance of just putting some basic math into play, and we wind up with this amazing cryptographic algorithm that every person on earth that's connected to the internet uses each and every single day. It's just really impressive. I wanted to go through the math on it. I would urge you, if you go buy a book on cryptography, I'll put a link for a manga guide to cryptography, but it's all going to wind up going down into these equations. So you've got to be ready to get out a pencil and paper and put your brain, apply your brain to these equations to get where you need to go. Anyway, if you've enjoyed this movie, I would ask you to please like it and subscribe to it, share it with others. You can drop in comments. I would love that if you would do that. And thank you for listening. Thank you for paying attention. And I'll talk to you in the next movie. Bye-bye.